So we're back. The impulse momentum theorem, delta P is equal to F net external delta T. We're going to do a little bit of tidying up on this notion and then go on to some applications. This part will be a little shorter than the last. So here we go. There's some detail missing here, so we need to add that detail. So delta P, remember, is just P final minus P initial. Now, I do want to show you some mathematical nicety with that. So that's mass final velocity final vector minus mass initial velocity initial vector. And we said oftentimes that mass is constant through an interaction. So if mass is constant through an interaction, I can drop the subscripts there. And then what you hopefully notice is I can factor it out. And then that term would just become delta V. And that's the way some people like to write the left side of this equation. They'll write M delta V is equal to F net external delta T. And that's a really nice thing too. It's very efficient for problem solving. Rather than individually calculating the momenta, they use that idea. So I just wanted to show that. It's not the main point of what I wanted to talk about. But what I did want to say is, remember what the utility of the left side of that equation is. That tells me I can figure out something about the force that acts on an object through an interaction. Very specifically, the types of interactions that we talk about are interactions that happen so quickly that they're very difficult to see. A classic example of that is a collision, right? And so if I have a brick wall here, and I have an unfortunate driver here, let's say there's no one in there, test crash dummies, we're not going to do anything nasty to human beings here, and our object is speeding along there with a certain initial velocity, and then it hits the wall, right? And when it hits the wall, what's it going to do? Well, there's a bunch of things that could happen, but let's say that in this case, it just crashes into the wall and it comes to rest. Now, in this problem, what's going on? Well, I have an object that is changing momenta from some value down to 0 because of its interaction with the wall. There is clearly a force acting on this object, and that's the force of the wall on the car, right? Clearly. And that's going to act to the left because the car hits the wall hits the car. The car is going to push the wall to the right, the wall is going to push the car to the left. Now, there are other things acting on the wall to hold it in place, which is why it might not go like flying off in the million directions. The car doesn't have anything else, right? So it's going to slow down. Now, I do want to focus here on this delta T. So what is delta T here? Well, in the last video, I said it is the time of interaction. So that car is driving towards the wall. Notice this force doesn't exist until the car makes contact to the wall. So this delta T in this example, delta T would be the time the car is in contact with the wall. Another way to say that is the time over which the car stops. Now, collisions happen ridiculously quickly. They're so quick that sometimes it's difficult to see what's going on inside of that collision. But by looking at the impulse momentum theorem, I know how fast that car is going before the interaction. I probably know the mass of the car. I know how fast it's going after the interaction, meaning when it comes to rest. Therefore, I can know the impulse that acted on that object without ever knowing the force that acted on that object through simple observation, which is really powerful. And that amount of time is really small, but that's actually a noble amount of time, especially in this day and age with photography. I can figure out how long it took that car to come to rest. That might be like 0.8 seconds, 1.2 seconds, some very quick amount of time, but that will let me know the force that acted on the car during that. I actually want to focus in on that force during things like collisions and very quick interactions. So I'm going to show you a video. And this video is of a golf ball hitting a steel plate. Now that golf ball is going 150 miles an hour to the left, which is ridiculously quickly, right? And this is being shot in 70,000 frames per second. So we're only going to see maybe like a 10,000th of a second. That's how quick this interaction is happening. But let's look and see what happens here. So right now, the ball you can see is not in contact with the plate. But let's just watch it. And it's incredible, right? That ball flattens out. And then it springs back, which is so weird because we don't tend to think that an object would do that, but it's happening at such a quick time scale that that's actually what happens a lot with objects when they interact with things at very small time scales, is that they deform and whatnot. But let's go back there and just look at that for a second. Again, it's just crazy, right? Right now, no force between the plate and the ball. But here's the weird thing. As the ball deforms more and more, right, what happens? Well, think about deforming an object. Like, think about deforming, an easy thing to think about deforming is a rubber band, right? The more you deform a rubber band, or even if you think about a tennis ball, the more you try and squish a tennis ball, what happens? Well, what happens is the force that tennis ball applies back to you increases. You have to apply ever more force to squish it by more and more and more. That force is the elastic force, right? And so this ball is experiencing an elastic force. And so that force during this interaction is non-constant. And remember, we said that we were only dealing with constant forces in this class. So, that force is non-constant. How are we going to deal? Well, let's go back to, Let's go back to our example there. And so we have that ball initially going in this way, and here's that metal plate, and we know it ends up rebounding and going in this direction, okay? If I pull it to the right positive, the initial velocity is negative, the final velocity is positive, but there we go. Most importantly, because there will be a force once they make contact of the plate on the ball, and that force is going to be to the right. It's going to be a positive force, all right? So why do I do that? Because what I want to look at is a graph of that force over time. So we know that that force starts out as 0 until it makes contact with the ball, or rather until the ball makes contact with the wall. Then we saw that force increase as that ball got squished and squished and squished. And then it starts springing back out. And that means the elastic force would decrease, 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 right? But it's happening over such a small scale, we're not seeing it. So this graph, when two things interact, always takes the following general shape. And that general shape is something that looks like this. Now, that should have more symmetry, and I apologize. I didn't mean to draw it without that much symmetry. Looking at that, that is a non-constant force. And we argued we're not going to be dealing with non-constant forces. So, but unfortunately, every time two things interact, there are non-constant forces. If you just push something, the second you make contact with that object, your finger smooshes a little bit, meaning that that force that you're applying is not a constant force. There's literally very few places in the universe where forces are actually constant. So does that mean that everything we've been doing is a lie? Well, no, we've just been making an assumption that the force is constant. So there must be a way to take these non-constant forces and represent them as a constant force, at least mathematically equivalent. And that's what I'm going to show you on this. So there you go. And so I've got this force that increases over time and decreases. there's always going to be some sort of maximum force. Let me move this up here, force newtons. And that is my max or peak force, right? That's going to occur at some point during the motion. Depending on the nature of the object, this thing might be symmetrical or not, depending how weird it is. But there you go. So this is what that graph looks like. So how can we deal with this? How can we deal with this? Because our equation, delta P is equal to F net external delta T. Well, there's my delta T from the time it begins interacting to the time it ends. So that is my delta T, that amount. But F net external, well, that's not going to be just that max value because it's only at that max value for an instant. So how do we deal with this? How do we deal with this? Well, what we realize is there must be a way to finagle here. So stop the video for a second, see if you can figure it out. All right, so hopefully you're back and you realize there must be some constant force that has the same effect as this changing force. And what's going to be that force? Well, that's going to be some force kind of like here, right? That some constant force less than the maximum force has the same mathematical equivalent as all of these. So how are we going to find out what that is? Well, we're going to use a little trickery here. I'm going to say that this force is the average force, right? That this F net external is actually F net external average. But how do you find the average of a weird function of force? Well, we're going to have another thing to think about in order to figure it out. Every time we introduce a new graph, well, every time we introduce a new quantity, I always say to you, is it a vector or is it a scalar? And we say, what are its units? Great. Every time we have a new graph, what do we think about? Well, we think about, well, what type of relationship is it? Well, looking at that, what type of relationship? It's kind of a weird one. Anyone know? Well, it's not a parabola because a parabola wouldn't have these weird bends like that. It's actually a bell curve or a modified bell curve, right? It's a very specific type of distribution, sometimes called a Maxwell distribution, sometimes called a Poisson distribution, depending on what it looks like. If you take stat, you'll actually see some of these curves. So it's a weird shape. I don't want to deal with the math of it. All right, great. The next thing we think about is, well, what's the slope of it mean? And so here, slope would be taking delta y's over delta x's, or in this case, delta f's over delta t's. Do I know anything that's delta f over delta t? Well, the answer is no, I don't know. There's nothing there. So is there something else we can talk about? Ooh, area. Area under the curve. Hopefully you remember when we did velocity versus time graphs, we found that the area from the trend to the time axis was the change in the object's velocity. Well, here, I can do the same thing. I can talk about this area. Now, the problem is you can't, we can't find that area. That area is not doable because of this weird shape. But what we're imagining here is, where is this average force? Well, look at this amount of the curve that's above this average. If I divide that in half, this average occurs when that area fills in there and that area fills in there, such that this red area equals the green area, okay? And if you think about that, well, what do I get when I find the area here? Well, that area would be that average force, yes, times the amount of time. Oh my God, look, it's the same equation. The area under a force versus time graph is the impulse. Okay? And so that's a fact that you're going to need to know. The area under a force versus time graph is the impulse. That's a really key idea, right? Notice here, force versus time, and we end up with change in momentum, right? That the area here is linked to a change in momentum, just like when we had the velocity versus time graph, the area underneath was the change in position or displacement. I think I said it wrong before. Sorry about that. So there you go. Change, important concept. Well, why is this good? Well, what this proves is I can take a non-constant force and represent it with a constant force that has the same effect. And that's what we're going to do for the scope of this course. And actually, that's what they do a lot of times when they're modeling things. When do we care about this max force? Well, actually, really only engineers care about that max force, because if we're talking about a car hitting something, or two things interacting, the max force will determine whether or not something breaks, the tensile strength of a material. So if I care about practicality, I care about that max force. If I only care about how is that object stopping, that average force is fine. So in physics, we deal with that average force, and in engineering, they deal with that actual force, and that max force becomes super important to them. So there we go. F net external average delta P vector. This is going to be our version of the actual impulse momentum theorem. We need to add that average bar in order to really, really make it make sense. All right. So some other ideas about this that are really important then. So notice then, if I have a force versus time, right? And here I go. And I have a certain area. If I take that same idea, right, but I do the same area, but I kind of stretch it out more, such that if this area 1 is equal to area 2, so if area 1 is equal to area 2, the reason is because the time for 2 was greater than the time for 1, yes? And notice here that if I were to look at the average force for 1 and the average force for 2, the average force for 2 was lower than the average force for 1. Well, why is that relevant? Well, let me just show you another quick video, and this is going to be the basis for all of the application work we're going to do on Friday. And so here we go. In my kitchen, I got myself a nice fresh egg. Uh-oh, garbage can, egg, garbage can, drop, and you'll notice what happened. Aw, the egg broke. Gross. Egg. Now notice here, I'm going to drop it from the same height that I dropped the other egg, right? So if two things fell from the same height, this second egg is going to be going just as fast as the first one. But it's on a pillow. Egg, pillow. And then, of course, I missed the center of it, but still that egg survived, right? And so, whoops. How does one egg survive and one egg not? Well, this idea is what's going on. So I had my eggs. There you go. Height. That means that each of the eggs, when they get to the ground, is going the same velocity, right? Galileo's law of falling bodies demands it. And what's the final state of each object? Well, this egg stops and breaks. This egg stops and lives, right? This is the pillow, and this is the basket, the waste paper basket, right? Well, why is that true? Well, hopefully what you figured out here is that if this one broke, it had to experience more force than this one. Well, why does it experience more force? Because if you think about it, these two objects are both going the same velocity before they hit. They were the same, pretty much the same. It was the same egg, actually. That's right. No, actually, I did take another egg. I should have done it in reverse. So you knew it was the same egg. And finally, what's the velocity of each object? Well, whether you splat or you fall on the pillow, the final velocity of both these objects was 0. These two eggs received then the same impulse, right? They underwent the same change in momentum. They went from moving to not moving. right? The same event happened to them. They stopped. In terms of physics, the event is stopping, right? Same event, stopping. But one egg lives and one egg dies. Why? Well, you may think to yourself, well, the pillow is fluffier and squishier, has more give. And that's right. But I can't put a number to give or squishiness. What I can put a number to is exactly what we talked about, which is time. The object slows down over a greater amount of time when it hits the pillow versus when it hits the waste basket. That's a very immediate change. And because the impulse momentum theorem, F net external average that they receive is going to be the ratio of the delta P to the delta T. Because these two objects receive the same impulse, the one that receives that impulse over a shorter period of time must have experienced a larger force. And that is a key idea, okay? That when the same change is going to occur in the motion, the longer the time to do that change, the less force that's required to do that change. So I want you to think about other examples of that being true, and those examples are going to be the work that we're going to do together in discussion at the end of the week.